Okay, so in last lecture, which was last Wednesday, we discussed why we want a multi-core processor. We started our journey from inline processor. We studied all the aspects affecting inline processor. Then to increase the CPI, we went to something called as a superscalar processor, where multiple instruction can be executed in parallel. And then, we went a step ahead, and we decided on a multi-core processor. That means we have to have a multiple processor cores on a same die area, like what you have as a quad core or octa-core. So we have discussed up to that point. We also discussed that why we need multi-core processor. He said that it was no longer feasible to keep on increasing the frequency just to get more and more throughput, because after a certain time, power is directly proportional to frequency. And if frequency goes beyond certain point, the power dissipation in a small area increases way too much. So that means you might be using only 35 to 50 to say 100 watts of power in a chip, but that is dissipated in a very small few square microns worth of area, and that would make the power density in terms of megawatts per centimeter square, and that is extremely hot, and it can burn the chip very easily. So we thought, or the designers thought, that now the future lies in parallelization. That you probably should make your work parallelizable, or all the programs should be able to divide in more or less large number of threads, and those threads can execute in parallel. Now this idea is good for some applications. There are certain applications which are known as embarrassingly parallel applications, and the first and the foremost which comes to mind is graphics and audio, because they both all work on matrix multiplication. So matrix multiplication is an embarrassingly parallel problem. So you can have as many threads as you like. As opposed to that, there are several algorithms which is serial by nature. So in that case, you can't execute too many threads in parallel. So right now, we have two types of philosophy which we are employing in our multi-core processor, which is there in our laptop and in our mobile phone. In first one, we use coarse-grained parallelization. So that means we throw different applications on different processors. So a processor core 1 might be reserved for, say, operating system use. Core number 2 might be using for download. Core number 3 you might be using for, say, C program or C++ program which you are executing, and core number 4 might be used for something else. Now that is coarse, and that's at parallelization at application level. But if you want to make something really fast, then a single application should be able to run on all 4 cores simultaneously, and that is, you can do it only if it is parallelizable. So take the example of graphics processor or GPU. Your GPU have got hundreds of cores in it, and all those hundreds of cores doing one specific task of graphics. Right? Rendering an image, it is being done by your graphics processor, and graphics processor is a special purpose processor, so that only quote unquote matrix multiplication kind of application goes in, and it can be threaded into as many cores as you have, and you get very good performance. Okay, so we talked about threads. We also talk about multi-threading on a single processor, and that also can give us some benefit. Why? Because you break down a program into number of threads. Now suppose one particular thread is stuck somewhere because of resource crunch. Say, for for example, say functional unit is not available, or your memory miss has occurred. In that particular case, you want to go into something, put that, or stop that thread from execution, take away control from that thread and put another thread in, and let that thread start working. So doing threading, you would learn this in system programming, and that would require, what you would be learning is a first principle approach, and that is done, using POSIX standard or something. But nowadays tools are available which will automatically thread your program, and you don't have to worry much. All you have to tell the compiler that from this portion to this portion, my program is parallelizable. Maybe because it's matrix multiplication or some such thing, and automatically it would thread into as many threads as you like. You just have to define, I want to divide this task into 16 threads or 32 threads or 64 threads or however many. So that is also possible. So multi-threading is not only for multi-core processor. Multi-threading can also give you some advantage on a single processor. Does anyone have any question to this point? Then I also told you that I'm not going to ask you too many questions on threads, because that is not the charter of this particular course. But this topic I just touched upon, because so that you can make connections with the topics which you are going to learn in system software, that how it affects hardware. I also told you the problem. So now we came up with the multi-core processor, and this was the first multi-core processor which was out in the market for general purpose use. So which was Core 2 Duo. You must see in some of the old desktops which you might have, or even some of the laptops, older laptops had this Core 2 Duo. So it had Core 1, Core 2, and two large L2 cache, and then you can see how much area it occupies. And then this is IBM Cell processor. It was sort of one major power PC over here, and then signal processing elements. There were 8 signal processing elements over here. So it was used mainly for broadband applications, so for communication purpose. So now then we came down to actual multi-core processor. The first one we discussed was centralized memory multiprocessor, where you can use few dozen processor, and second is physically distributed memory multiprocessor. So this is what you generally have. This particular figure is what you generally have in your laptop and your mobile phone. So here you have so many processor cores starting from P1 to Pn. Each processor core has its own cache memory. Then it is connected through this interconnection network to a single centralized memory. I told you last time also that you can see this separate boxes of M written over it. Doesn't mean that all these main memories are separate. They're just banked main memories, and your banking of the main memory is done so that you can simultaneously pull out maybe 8 or 16 data from them in parallel. So if you have 8 such memories in parallel, then you can have 8 data words going out simultaneously. So this is a centralized memory, and this is for use mainly for distributed system. So this is like distributed computing. Have you guys heard the name of Project SETI, S-A-T-I? Okay, the Project SETI was used by Uh, in fact, it is still in use, and they want to find out extraterrestrial. I mean, they have got huge array of antennas, and they keep on listening to signals coming from outer space. And they feel, or we all feel that there has to be intelligent life out there somewhere in this universe, and probably they are trying to communicate with someone or anyone. And if we can catch those signals, we can analyze them and send it back. And it requires a lot of analysis, because a lot of radio waves keeps on coming. Some of them are coming from stars, that planets. Some of the signals are coming from breaking up of planets. And so each signal has to be analyzed, and for that it requires huge bandwidth. So Project SETI, they came up with some interesting experiment in Berkeley, that they requested people to give the bandwidth of their mobile phone. So it worked like this. So you donate the time and processing power on your mobile phone when it is not in use. So what they would do is that once you give the permission, part of the processing, they would break down the problem into several parts. And then there would be a lot of redundancies, and each problem would go to, say, thousands of mobile phones. And there were also conditions set up by the person who has donated his or her time on the mobile phone. So a person who has granted permission may say that you can use my phone only when I'm not using it, or that means if there is no other application running on this phone, you can use the processing power of this phone. Plus, you can use it only when the battery is above 50%. If it goes below 50%, then don't use it. And there could be many conditions. So they would put a lot of redundancy, and same piece of code would be sent to, say, 100 phones. And some phones may pull out that because here the processing limit or the power has gone below 50% in battery. So that's why that calculation has been terminated. Or in this particular phone, suddenly users started using the phone and started checking the WhatsApp or email or whatever. So that's why that process was terminated. But then if you have got so much redundancy, at least some of them would be able to complete their work. And then that was the prime example of distributed computing. And then all the results would be put together, and they would do something. In fact, multi-core processing, before we go into the last part and the nitty-gritty part of it, it was originally designed or used first in Hollywood. Hollywood film industry is not just for entertainment. A lot of computer science has gone into it, and in fact, they are the biggest user of technology. All of you must have seen the movie Titanic, and in Titanic, you must have seen the scene where the Titanic ship breaks in the middle, and this was almost at the end of the movie. And then the one end goes up like this, and the other end is like this, and then you can see people sliding down from this end and falling into the water or on the deck which is below. Now those kind of special effects, they wanted to do. Of course, they would not get real people, who would volunteer for such things, no matter how much money you give them. So of course, it has to be done by computer-generated images. So the producer of this film went to a company which is specializing in special effects for movies. Now this company told them that to do this kind of stuff, you will have to employ services of a supercomputer. Supercomputer I'm talking about of 1990s. That that supercomputer would give you the bandwidth and the required computing power to render the lifelike image, what you are looking for. Because in the movie, if you feel that if something is like shaky or jerky, or it is not smooth or not fluid, immediately your eyes would catch it and say, okay, oh, this is not real. I mean, to give that the viewers a thrill, things have to be very smooth. And also your image is going to blow up into this huge screen, and so that even the smallest mistake viewers can catch. And the time for the supercomputer was very expensive. Now what happened that in 1988, a person, two people from Lawrence Livermore lab, they came and made a prediction that till 1988, all the supercomputers were made using specialized chips. So companies like Fujitsu and NEC were designing the chip for supercomputer. They were designing operating systems specific for that particular chip. So everything was proprietary. And because of that, everything was expensive. These two guys from Lawrence Livermore lab said that from now onwards, all these supercomputers will be made from equipment which is available off the shelf. Which means that I can go to a good dealer, say in Ahmedabad, and say I want 100 Intel Xeon chips. And, he would be able to give me that. And if I can make a cluster of 100 Xeon chips, I can make a supercomputer. Plus, the operating system would be Linux, so that is freely available. And what made this possible? This was made possible by designing something which is known as Beowulf cluster. So BAEWULF, Beowulf cluster, you can do Google search. Now this one, I can give you a recipe of it. I can show you how you can connect two laptops in parallel and execute one program on both the laptops by dividing up some work on laptop A and some work on laptop B. I mean, you can scale this problem to hundreds of laptops and desktops. So this Beowulf cluster was first used by this Hollywood special effects company. They made a cluster of 256 Linux boxes. They put them together and created this, and made their own supercomputer and made this amazing special effect. I don't have to tell you how successful it is because you all must have seen it. And at no point it felt like computer generated. It felt like it was real. So the power of computing has become real by this simple idea that you can connect hundreds or thousands or tens of thousands of Linux boxes together and make it like a one system. And that was something which is known as sort of distributed computing, because your laptop is like one self-contained system. It has got its own processor, it has got its own cache, it has got its own main memory. Then second one, if you're interested, I can give you this recipe. So you, along with your friend, all you have to do is install Ubuntu on your laptop. And you can connect two laptops and run a program, a simple program. I can also give you a program which is a calculation of the value of pi using Monte Carlo method. So that uses lots and lots of calculation. You can divide up the task between two processors. Between two laptops, and within laptop you can divide it up the work among the 4 processor cores, right? So you can use 8. And the fastest supercomputer nowadays is made up of simple Intel Xeon chips. Intel Xeon chips are chips which are much more powerful than i5, i7, and i9. They are used in servers. But you can still go and buy them in the market. They're available off the shelf. You don't have to make a special chip for that. And all the people who have made this supercomputer, like China has got the most powerful supercomputer. They have connected 300,000 such Intel Xeon chips together and made a supercomputer. So you guys can make a supercomputer by connecting your laptops, or you can buy Raspberry Pi boards. So if some of you who are like very innovative, or are interested in doing it, you can connect, I don't know, 4, 8, 16, 64, however much money you have or however much resources you have. you can connect those boards together and send in the program, and divide the program into as many parts as many boards as you have, and you can do things faster. So this is the whole idea behind this. But right now we are concentrating on this, the first part, that is centralized memory multiprocessor. This idea, if you want to experiment on Beowulf cluster, someone can do if some of you are interested in creating this Beowulf cluster of just 2 laptops, because it will teach you all the aspects of your program in one shot. It will teach you about operating system. It will teach you about networking. It will teach you all the principles of system software. It will teach you all the problems of multi-core processor. It will teach you all the aspects of multi-core programming using MPI and OpenMP. So it's all coming together. And once you do it, probably initially you may just follow the recipe, and you get things, and then you start wondering that okay, I was asked to do this, but why? Then you can go deeper into it. So if you master how to do Beowulf cluster by actually understanding it, basically that means you have understood your whole BTech ICT program, most of it. Okay, but coming back to the centralized memory multiprocessor, we have a limitation on how many cores we can have. Here, we have said, we can't have more than few dozen. So in reality, right now we are stuck at 8. In some, the later ones, even the server class chips, you have got 32 to 96, but that is still a few dozen, not more than that. The main reason for that, and the additional problem which we will face in a multi-core processor, apart from all the problems which are faced for inline processor and superscalar processor, the additional problem which we face here is the cache coherence. Because there are multiple processors, each processor has got its own cache. They are using a same main memory, and this processor core may change some value of a block, say block X, which is used by say processor P1 and processor Pn. And processor P1 changes the value of some word in data word in block X. Now, how would Pn know that that particular value has changed? So, otherwise, if it doesn't know, if there is no way of knowing, then it will be too much. So, what it does is, as soon as the value here changes, it will do something over here and raise a flag, and we are going to study that in this class, what they are doing. But this is known as snooping protocol. Snooping means spying. So all this processor will keep on snooping, what's happening, what kind of data is flowing through an interconnect network. As soon as PN says, oh, I changed the value of, say, block X, it will put this message over here. And whichever processor has got this block X in its cache would take notice and immediately change the status of its X block and say, okay, don't use it because, now this is an old block. So that is about it. The reason you can keep only up to a few dozen processors is that, the traffic on this interconnection network will become too much if there are too many processors, because every time some block is changed, they have to put the word on interconnect network. And then, apart from this, there is also traffic coming from main memory going to various caches. So because of that, there's a limiting factor is interconnect network for this centralized memory processor. It is also known as symmetric multiprocessor because, the distance or the time to connect to main memory from each processor is the same. right? So that it is going through interconnect. So it is a symmetric. Here it could be asymmetric. Why? Because this one main memory is here. Suppose Pn want to access the main memory of P1. It depends on the distance. If it is P2, then it is close by. If it is Pn, it is far away. So this is basically asymmetric. This is symmetric. This is communication is that how do you pass a message that you can communicate either through message passing between multiprocessor, and this is an old program. If you use look into the something called MPI, message passing interface. So what I do in my Beowulf cluster is I use two protocols, MPI and OpenMP. They are nothing but protocols. And when I have two laptops, the MPI protocol would distribute work between two laptops, and OpenMP will distribute work among the cores of each laptop. So if there are 4 cores, OpenMP protocol would divide work between this 4 processors of laptop 1 and laptop 2, and MPI would divide up the work between laptop 1 and laptop 2. So there is message passing interface, which is this. This is one way of doing things. And second is the shared memory multiprocessor, which we have discussed. So you have got uniform memory access time for shared addresses and non-uniform memory access time. So your UMA is the same as centralized multiprocessor. So we are going to concentrate on this. So basically, these are the same names. So UMA and SNP and this centralized memory multiplexer is the same thing. You can call it by different names. Okay, so we are going to see a snooping protocol. Once again, why this snooping protocol we are doing? We are doing because now the only problem which we have is how to maintain cache coherence. Cache coherence means one processor has updated its cache. At what time other cache would have the same value? Should they have it right away? Well, it is not necessary. It's like, the whole idea about write through and write back. But, in write through, you say that, if one level of cache has changed the value in a particular block, it's immediately the next memory level should also get it done right away. Now, it's a simple protocol that once you do it, you don't have to worry. But on the other side, you may think that, probably you may not have to use this value again because, suppose if it's a value of a counter. Now, counter keeps on changing after every execution of 5 instructions. So, counter will go from 1, 2, 3, 4. So every time when counter value changes to something, you don't want to go and change it in the next memory level because it's waste of time, right? So in that case, you think that, okay, write back thing is much better. So very similarly here, in cache coherence, you do not want to change, say if processor 1 has changed the value in its cache, you don't want to go and change it in other caches. Because, you can do it, of course, it would make things very simple, but it will be so time consuming that, your efficiency will go down. So they have come up with new type. Now, you can read about this memory coherence and consistency. I'm not going to do it. I have given a lot of examples over here, but I'm not going to hold you responsible for coherency and consistency and knowing the difference. This thing, you would automatically start understanding when you start doing systems programming and operating system. So I just wanted you to be aware of these two words, that there is something like cache coherency and cache consistency. But right now we are only going to concentrate on cache coherency. So when other caches are going to see the changes which has happened in a particular cache. So let us go down to the snooping protocol. So only thing, I want you to remember here is the snooping protocol, how that works. Now you will be happy to know that, one Mr. Janak Patel of UIUC was instrumental in coming up with this MESSI protocol. Now MESSI protocol has got 4 flags to be given to each block. Now a block can get M flag. M means modified. Second flag it can get is exclusive. Third flag it can get is shared, or fourth flag it can get is invalid. Right? So a block can have either of those 4 flags to it. It can have M flag, E flag, S flag, or I flag. Now, just like when you said in the write back protocol, there are only 2 flags: dirty or not dirty. Not dirty means 0, and dirty means some value has changed in that block. So you get value of 1. Here it is slightly more complicated. So instead of just valid and not valid, you have got 4 flags, which is modified, exclusive, shared, and invalid. In the recent ARM processor, they use MoASI protocol. So there is one additional state, or the 5th flag, which is owned. We are not going to talk about it because it is not putting too much new thing. It is more for administrative purpose. So MESSI protocol, if you understand, you will understand cache coherency, and you will understand the functioning of a multi-core processor. Okay, so there are 4 flags which can be given to any memory block which is there in any given one of the processors. Okay, so let us, there is a lot of things which are given here in table, but I believe that things you can do or understand better is from example. So I'm giving you an example. Okay, let's see. There are, say, processors P1, P2, P3, and P4. There are 4 processors. It's a quad-core machine, and this is your main memory. Okay, so the one in red is your main memory, and all these are your caches of different processors, P1 to P4. If you are a very computer science buff, then you call it P0 to P3. I think let's say P1 to P4. Now look at this particular case, and every time I would refer to what P4 is demanding. Okay, so let's say this is P4, this is P3, this is processor 2, and this is processor 1. Okay, now processor 4 wants a value of a word which is in this particular, say, data word x equal to 3. It wants that value, but as you can see, the current value in main memory is x equal to 5. Okay, so this value obviously is not the correct value. If you look at here, all other blocks have updated value. So from the example which we have seen, or from the protocol which we have seen, when multiple processors have their cache validated with the updated value, they get S flag. So this particular block has got S flag, that means shared. And so this one is invalid because it didn't have a chance to update it. So it is getting the flag of I. So as soon as the P4 makes a demand for this particular data value to get the value of X, it would say, okay, you can't take this value because it has got invalid flag to it. Because it has got invalid flag, it will have to go to main memory, bring the value back in here, and then it has to use it. So this is, what is it doing between this and this? It is using, what is it using? Right allocate or no right allocate? it is sort of like right allocate. For reading, it always has to be right allocate. For writing, you can do differentiate between right allocate and no right allocate. So it is bringing the x equal to 5 here. As soon as it is updated, its flag of invalid will change into S, that means shared. Okay. So let us once more going over this problem. P4 wants to read something. All other processors, this particular block value of the word X is 5, and they all have a flag of S. Means these are all shared and current, and the main memory value is also valid and current. Only this thing is invalid because it has got old value. So the protocol is copy this value from main memory, get it into the cache of P4. Now its flag will change from invalid to shared because now all 4 processors are sharing that value. Okay. Look at the second example. This example is interesting. It is using a flag called exclusive. Now you use the flag exclusive only when this particular processor cache and the main memory have the most current value and no other processor has that current value. Okay, so look at here, I'm using this flag E. And I want to give you one heads up. Suppose if this was also old value and this has just recently changed its value so that they didn't have a chance to update either main memory or any other caches of the processor, then this one would be, this flag would be modified. That means the copy in this one is modified and no other processor cache, that means a cache of P2, cache of P3, cache of P4, or the main memory has it available. So if M flag was there, then all these would be invalid. But when the exclusive flag or E is there, it simply tells you that this processor and main memory, it has got the current value. And if this is exclusive, then of course, by definition, no other memory block can have a current value. So they have to have I. You can't have S over here. If this and this have the same current value, then exclusive flag would change into S and S over here, just like here. So, okay, this is the first situation that, again, P4 wants to read a value of a word X. It sees that, it's got invalid flag to it. What it does is, then, it has to go to main memory, bring the value of X equal to 5 to there. Now you can see here. Now the flag of this P1 cache has changed from E to S because now it's no longer exclusive. Now it is shared because it is shared between P1 and P4. And these two are still invalid. Right? So this is how you do read. Does anyone have any question?
Can you explain again for modify?
Okay, I will come to this modified example. It is coming next.
Okay.
Yeah, but so then I will once let me go through the whole example and then I will go through it once again. Okay, this is the example of modified. In this example, again, my P4 processor wants to read this value. This value has got invalid flag, so it is no longer valid. It even can't go to main memory. Why? Because this processor has got M flag. What it means is this processor P1 has very recently changed the value of X in its block. So all these blocks are the same block, but this processor has changed the value of a word within that block. So I'm looking that word within that block contains the value of X. It has changed to 9. So this one has got a flag of M. All others are I, and this is also invalid. Main memory block is also not the current one. And this one remembers what flags the other block stack. As soon as it knows that this one sends a request, it says, main memory says, I can't supply you the current value till I modify myself first. So what the second step would be that this value would be copied into main memory. Okay. Once it is done, what flag will come here?
Exclusive.
Yes. So now the flag here will change from modified to exclusive, because by definition I can give the name of exclusive only when a block in a given processor, say P1, and the main memory are current. And this would get what flag? These are still invalid, invalid, invalid. Now, in the third step, now this particular block would see, or particular processor, a cache would say, okay, now the value in the main memory is current. So I'm going to get the value from here and bring it to me. Now you can see, now it has changed from exclusive to shared. Why it has changed into shared? Because more than one processor cache have got the current value. So now it is no longer exclusive flag, but now it has become shared. Is this clear? Does anyone have any question?
Sir, I am having a question.
Yes.
Sir, if it happens when the core of that cache attempts to read that block, right, sir?
Yes.
Sir, but sir, if it is invalid, then will it always go to the memory for the correct value?
Right.
Sir, my question was that, but in going to memory, it will take much more time than just communicating it from other cache, right, sir?
Yeah, so I think what you are talking about is there is something called as a own state or MOESI protocol, MOESI, and they allow the exchange between processor cores so that you don't have to go to main memory. So it is, yes, it's a valid thing, but this one was the first one and makes things much simple. So initial processors, multi-core processors which came, they were using MESI protocol, and in that MESI protocol, you were using this kind of thing, that the modification has to be made. I mean, the most current value eventually has to come to main memory. Only then it can be passed on to other processors.
Okay, sir. Okay, sir.
Right. So what you are saying is possible and correct, but I mean, this was one which just, it's like, why use write through at all? Why not just use write back all the time? But then write through would make things very simple. So you don't have if you don't need any complications in your design, and if you want your design to work really good all the time, then you would use write through. It might not be optimum, but it is simple. Okay, does anyone have any question on this? Okay, so now we are going to see the write miss. Till now, we were going to doing about read miss. So we saw 3 cases in read miss. In the first one, this was the only cache, the P4's cache was the only one which was invalid. All other caches were valid, right? So they had shared flag. If more than one processor has got the most current value of a particular block, then they get S flags. So here all 3 of them, except the 4th one, have the most current value. So they all get S flag to that particular block. So this one will have to go to main memory. update itself, and now all the blocks have got S flag. The second example was that, up till now, this particular flag has just corrected its value, and it had time to go to main memory and write it back, right? So it has written this value into main memory. So once it is written over here, so when main memory also has the most current value along with only one of the group of processors, then this block will get exclusive flag E. And then this block first, when it sees that one of the blocks has got E flag and it has got I, so then it will go to main memory and bring in the latest value. And as soon as it does that, the flag of this particular block for this particular processor will change from E to S, because now more than one processor has got the current block. And the third one is the third case where this processor P1 has recently changed the value of a block X in its cache, and it didn't even have time to update it to main memory. So this one would say, okay, I want to read it, P4. Immediate request has come to P4 that I want the value of X. So the memory controller would stop it and say, no, you can't cache the value from main memory because this does not have the current value. So it will have to make this current first. So now the flag for the that particular block in cache of P has changed from modified to exclusive. Then when that happens, now this block can go and copy it from the memory. It copied it. So when it copied it, suddenly the flag for this particular block in P1 changed from exclusive to shared, because now this cache of P4 processor also has the most current value. Does anyone have any question in this? Okay, so now we are going to do a write miss. In write miss, suppose the block which P4 wants to write, let's say this is P1, P2, P3, and P4. Now P4 wants to write into a particular block. Now that block is not here. That it is not there. That's why it is write miss. Now it would look around and talk to main memory that and let's say we have got the kind of write allocate thing. It says, no, sorry, you can't take this block because this block is not current. So first, what you have to do is write the value of X into main memory. So now what flag will this have? This particular block, it will change from M to
Exclusive.
Exclusive.
yes. This block will have
I.
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 I. Yes.
Okay, this one will not have any flag because that block is not there. So I'll just written I over here, but in fact it is not correct because that block is not there. So first you will have to do this. It will have to correct this value in here into main memory, X equal to 9. Then you allocate it. So now you bring it into this, and then this wants to write a value. So this one, once you do this, what will the flag here at this step? What will be the flag here?
Shared.
S.
Yes. Shared, again invalid, and shared. Now you have brought that black block into the cache of P4, and now you say to P4, okay, change your value. So now it has changed the value of X from 9 to 10. So now again, the flags would change. This one would get modified flag. This flag would change from shared to invalid. So these three caches will have that particular block marked as invalid. And this is modified because it didn't even have time to change into main memory. So some of you may wonder that why take pains to change the value in the main memory first, update the main memory with the old value, and then replace it with a new value. Then why can't just wait and the new value of X equal to 10 it is written and then put it into main memory, so that this one step in the middle can be avoided. But according to the principle of computer science, it is not a good idea to change the values just like that. So main memory should change the value of that particular block in the order it was changed. So no step should be missed. So you can't say that I don't want to update the value of X to 9 because anyway it is going to change to 10 very soon. So I don't want to write it. No, it doesn't happen that way. So that's why this is the fourth step. Does anyone have any question in this one?
Hello, sir.
Yes.
Sir, each step takes one cycle, or all this whole thing is done in one cycle? Like flags are changing, writing back, and all this will be taking different cycles?
Well, it's a good question. It depends how fast or how you have designed your processor. So, if it is taking more than one cycle, then, probably what to speed things up, they would change your memory into divided into 4 parts. So say, if you're making an inline processor, so, I'm just giving you an example. This is not a right example because I'm doing inline and talking about multi-core. But let's just say 4 cores, and this is your memory cycle, and this is your memory cycle. And if you want to make this fast, and when this process is too long, then you allocate them 2 cycles. So 2 fetch 1, fetch 2, and then you call it data memory 1, data memory 2. So overall it may take 2 cycles, but things now would be working fast because this would not be too big, so that it is stopping the time for everything. So yes, it depends on the designer, that how you want to design it and how many cycles it would take. But if you want to go and what it is written, totally 4 cycles would be required, right? So first would be a write miss, right, for P4. That's the first one. Then it would say, what do I have to do? Do I have to go to the next lower level? It will contact main memory, but before it contacts main memory, it would say, okay, don't look for it here. I want to update myself. So in that particular cycle, the value of main memory would be updated with the quote unquote old modified value. So modified value was X equal to 9, which was modified by P1. That value will be written into memory. Second cycle. Third cycle, you will bring the value, that particular block where P4 wants to write. So you bring it from main memory into processor 4 cache, and then in the fourth cycle you write. Does it make sense?
Yes, sir.
Okay. Okay, so this is the last topic of this multi-core processor. I want to give you some general idea. Probably now, this is the right time to talk about those issues. And that issue is this. So, I have been visited by two vendors, and one vendor tells me that I got, say, processor A, which is running at 1 gigahertz. And another guy comes in and tells me that he has designed processor B, which is running at 2 gigahertz. Now, if this is the only information I have, can I make a judgment that which processor would be giving me or would be finishing my task? I have got the same program to run here and here, right? So I mean, both of these processors, I'm going to put the same test program or benchmark program or application of your choice. Put it to both processor A and processor B. Only information which I have is a processor A is running at 1 gigahertz, processor B is running at 2 gigahertz. Can I make a judgment that which processor would be able to finish my task faster?
No, sir.
Why? Answer could be correct, but I want to know why.
Sir, it may depend on chip architecture and other things also.
Okay, can you elaborate, please? Okay, so probably I can tell you this, that suppose I have divided my work into 5 parts. Right? And this is, say, 1 gigahertz processor, and in this particular time, which is, say, 1 nanosecond, approximately, I'm just disregarding other values of setup time, hold time, clock jitter, and everything. I'm just removing that, assuming it is perfect and it is 0. It's all the time is used only by computation by gates. So 1 nanosecond, and so on. Now, it may happen that this particular processor, the way it is designed, might be able to do much more work in 1 nanosecond than this processor is able to do in half a nanosecond. Right? So it may have to do this. It may have designed a larger number of pipeline stages. So it may happen that 1 gigahertz processor is working as fast as 2 gigahertz processor. So just by looking at just the gigahertz value, you cannot tell that processor A is better than processor B, because you need to know other details. So one should not go only on gigahertz value that okay, this is Intel processor X, which is running at 1.5 gigahertz, and this is AMD processor Y, which is running at like 2 gigahertz. So which one is better? Insufficient information, you can say. Does it make sense? Okay. Any questions up to this point?
Sir, is benchmarking sufficient to get this information?
Well, see, benchmarking is never sufficient. When you use statistical model, most of the people have problem against statistics. So, statistics is something which would tell you that, if your feet are in the boiling water and, if I put a block of ice on your head, the average temperature that your body is experiencing is normal. Well, I mean, it is not correct, because, your feet would burn and, your head would get freeze. So statistics can never give you a correct answer, but then, you have no other alternative. So benchmarking is only thing, which we have to go by, because I might purchase the laptop and you might purchase the laptop, and I might be using my laptops for different things than what you might be using. So how do we know that particular or how do we know the figure of merit? And to know the figure of merit, they have come up with an idea. So let's assume that these are the popular programs. They may say everybody uses, say, internet browser. So all the program content, which is used in writing internet browser, they would give a major chunk to that particular thing. That in this test program, there would be more lines, which has something to do with internet browser. Then in graphics also, it will get certain portion. Then some people, because everybody likes to do graphics because people like to see YouTube, WhatsApp, Instagram, and then so on and so forth. You divide up the work. So then you make one package in which so many lines are like internet browser type of work, then graphics processor kind of work, and so on. And so then it becomes a benchmark program. Well, benchmark program is benchmark program. Nobody's doing work exactly according to that thing, but okay, you have to trust something. So benchmark program is something that you use. And also, if you want to compare processor A with processor B, the only way you can talk about it if there is the same program, which is running on both. In fact, benchmark programs, people have gone to court. Like there are benchmark programs from spec, like SpecMark is one thing. Then there is a cafe. Now there are lots of benchmarking program. And benchmarking program is supposed to come from impartial organization. So Intel cannot make its own benchmarking program and say, this runs very nicely on my processor. So usually what happens is the benchmark is done by an independent entity, which is not involved into designing of a processor. So I think AMD went to court against this benchmark designing program because they said that you have designed the benchmark program with an instruction mix, which is more amenable to Intel architecture, because Intel had worked hard to improve those parts, because in architecture, if you try to improve one thing, the other thing may go down. So if I write a program which is skewed towards one thing, favoring one, that, okay, I'll put more instructions for which this particular company has optimized it. And, the non-optimized part or instruction, I'll put less of it. So then, the Intel processor would look really good as opposed to AMD. And, it may look good, which is not the correct story. So yes, benchmarking is a big thing. It's also a big politics, but that's what it is. Anything else? Okay, so now just let us quickly talk about the exam part. We are going to have our exam on 16th of December. I'm going to put 20% weightage on ARM instruction set architecture. So at most 20%, not beyond that. Rest of the problems will be from your implementation method. So starting from pipelining to multi-core processor. Also in superscalar and multi-core processor, not too many questions are there. I may ask a question of ILP, which you have done in your lab. So that kind of problem may be asked, but there's no guarantee that will be asked or not, because there are many other kind of problems which can be asked. Also, I may put different versions of the same problem, and that is possible through metal problems. So please do not copy, because then you may end up copying wrong answer. And so that might be hurting you. Also, as always, as I told you in the first midterm, also if you know this subject really well, then it is in your benefit not to pass on the right answer to everyone, because I give A grade, or for me, A grade to high BB grade are really precious. Other grades I don't really care that much. But if you want to get AA grade or AB grade, then you have to really stand out. And stand out means you should be apart from rest of the students. So if you are a good student and if you think AA or AB or BB grade is something you want to get, then don't pass on the correct answer to everyone. Otherwise, you would also be part of them, and then I may decide to give very few AA grades because then everyone is bunched together, so I cannot separate people out. So if you are very smart, do not pass on an answer to people. Also, these students, when they check correct papers, I may ask a question, which the papers may have to be manually corrected. So if they see the answers are coming out same, it's very easy to pick it out. So then, both people will get 0 marks. So whether you are the one, who actually knew the answer and did it, another guy who did know the answer and, copied the same thing. And if it is same, then, both the people would be punished, and you don't want to be punished unnecessarily. I will put my slides. Someone has asked in chat that, I will put my slides on branch. Lecture number 6, branch prediction. I think I have put those slides. I have passed it on by mail. I'm not sure, but I will do it, and I'll also put this slide set. Do you want a revision lecture on Wednesday, or you want to stop here? Okay, let's do one thing. I'm sure you have got a student body on academics person. I think some Aditi Das is the one who is, I may have forgotten the name. She is the class representative. So you decide amongst yourself and tell me by tomorrow whether you want a lecture on Wednesday or not. That lecture would be a revision lecture. If you are not interested, then I will not hold a lecture. Otherwise, I've already given you a link, and then I will conduct the lecture on Wednesday. So please let me know one way or the other. It's a responsibility of the class representative whether we should be. I mean, you can decide. You can pass on Google form or whatever. Any question from your side? Okay. So we